All right, hello everyone. Welcome to today's installment of the Corundum developer meeting. Thanks for tuning in. All right, let's see. So today, just real quick announcements and status updates. Announcements: the next Corundum developer meeting will be in 2 weeks on July 17th. The next Switch developer meeting will be on July 10th. Now, obviously, unless something comes up, those should be the dates and times for those. Okay. Moving on to the status updates. Basically just 4 things for this week. Not a whole lot to talk about. The PCI Express buffer management, hopefully the final installment of that. Then I also updated the Upstream Git repo for Corundum with a bunch of basically accumulated changes since the last time that was updated. I'll go over those real quick. I also have a couple of upcoming changes that are potentially somewhat breaking, more on the driver's side, I think, that I'm going to talk about real briefly, just to give people a heads up there. Mainly applies if you've written an out of tree DPDK driver or something like that. Otherwise, it shouldn't really be a big deal. And then finally, a couple of notes on basically the current thing that I'm working on, which is the Mac control layer and PFC components. All right, so moving on here. So PCI Express buffer management. I'm not going to go over this in too much detail because, you can look back at the last couple of developer meetings. I've talked about this stuff a couple times already. But the gist of it is that PCI Express endpoints have to advertise infinite completion credits to prevent deadlocks, but that means you can't apply any back pressure against incoming TLPs on RX. Different PCI Express interface cores. In this case, we're talking about specifically the hard IP core that provides a transaction layer interface to the user logic in the FPGA. That has to provide some amount of RX buffering. But if you have to advertise infinite completion credits, then you can't, exert any back pressure against the incoming link to, slow down traffic there. Instead, you have to manage how many read requests you've issued to make sure that you don't overflow the buffer. Previously, the Corundum DMA engine didn't implement this, and I've run into this a few times, I suspect. So fixing this is definitely something that needs to be done. So it's one thing to actually fix this in terms of implementing logic in the DMA engine to keep track of, the number of outstanding requests and the amount of outstanding data to make sure this buffer doesn't overflow. But the other component of this is you actually have to know how big the buffer is and how much stuff you can store in it to set those limits appropriately. So I've done a bunch of testing on several different FPGA boards in 2 different computers that I have lying around here, including a very old box, an AMD Phenom CPU that actually seems to be behaving in a way that's useful for these tests. The idea being to measure how much data we can store in that buffer. So the methodology is pretty simple. I made some adjustments to the DMA example design in the Verilog PCIe repo, and I've actually pushed these modifications up to the to that repository. So, and it's now part of the example design. If you run it, it does the completion buffer management tests as part of just the basic operation of the in addition to just testing the DMA operation. But yeah, the idea is to stop reception of incoming TLPs in the core for a while, then issue a bunch of DMA reads, and then release the block on RX and see if any completions got dropped. In which case you'll get a hang because the DMA engine will be waiting for something that that got dropped. Relatively straightforward idea. And then I also added a couple of additional counters so we can see exactly how many completions got issued. And then tested this on 2 different computers. One of them, a more modern machine with an Intel Xeon 6130 CPU that is relatively well behaved and generates, effectively as large completion TLPs as it can. And then the second one is a rather old AMD Phenom CPU that tends to like to generate 128 and 64 byte completions in response to various requests. So the nice thing about that is if we can get it to reliably generate 64 byte completions, then we can test the size of the buffer in terms of how many completions it can store more effectively, because we can only issue up to 256 read requests at a time in most cases, because you're limited how many tags you can use on the PCI Express interface. All right, so the results of this testing. This is a rather dense slide, but I'm just going to go through this data at a high level pretty quick. I've tested basically 4 different FPGA boards in the 2 different machines. Most of actually in 2 of these, I guess I only tested it in the one machine. On the Xilinx ones, there was a bit of a question as to exactly what gets stored in the buffer. So I tested it at both 256 and 128 bytes on the completion end, just to see if we could figure out whether both the completion data and the headers are being stored in the same memory. So the numbers here for the first 2 blocks here are exactly what I reported the last couple of weeks. But what I extended the test by also running on the Stratix 10 MX and Agilex F devices, mainly just to make sure that the numbers I was plugging in there were correct and that it matched what the datasheet said. And it's a good thing I did, because turns out the numbers for the Stratix 10 MX were also a little bit off. But we're going to go over this real quick. Okay, so for the Kintex UltraScale devices, or for the UltraScale series, I tested a Kintex UltraScale device, and this lists in the datasheet 64 CPLH and 16384 bytes. Instead of listing CPLD credits, even though the table said it should be in credits, it listed it in bytes, apparently. So if we run this on, and that corresponds to 1024 completion credits for reference. So at on a machine with 256 byte completions, that resulted in a hang after we went beyond about 960 completion data credits. So we're definitely hitting the data buffer size, not the completion buffer, because that has 60 completions, because that resulted in 60 completions being issued. So since we only hit 960 instead of 1024, if we run the numbers, we're definitely running into a limit with both the completion headers and the data stored in the same memory. If we go to the machine with 128 byte completions, then we can only fit 64 completions in memory, which matches what the datasheet says, and that corresponds to only 512 data credits. So we can only use half of the memory, or half of the buffer on that device. And then I figured out if we send a read request, which basically crosses 2 RCBs, this old AMD Phenom machine actually produces 4 completions. So issuing some of these read requests, we hit a limit after 68 completions. So it's definitely indicating that we can store about 64 completions or so, and around 1024 data credits once you factor in both the completion, the size of both the headers and the payloads. So what I ended up doing for the UltraScale devices is I set the data credit limit to basically the header credit limit, which I think is going to be about 1024 minus the number of completion headers that are available. So that one seems to be about right. And then moving on to the Kintex UltraScale Plus devices for testing with the PCIe 4 IP core. We get basically the results that we would expect. For both machines, we hit the completion data limit here, indicating that we can actually send a lot more than 128 completion header credits, because in this case, with the with the AMD Phenom machine, we were able to store about 230 completions inside of the FPGA. But that corresponds to about 1,800 data credits, which, overran the buffer once you factor in the headers. With these unaligned operations that result in a large number of small completions, I was able to get 268 completions in the buffer. I don't know why this is a fair number more than 256, but that definitely implies that we should be able to store around 256 instead of 128. So that's good, because that's going to be a little bit better for performance. We can actually use more of the buffer on UltraScale Plus than we can with UltraScale. Like I said, I removed the slide in this presentation, but for UltraScale, we can only fit 256 bytes of completion data per completion inside of the buffer. So that means that we can only use a quarter of the buffer worst case. For the Xilinx devices, you can fit 128 per completion, so that means we can use about half of the buffer, because we have to factor in worst case 64 byte completions. Right. So in both cases, that's going to result in potentially some performance degradation, but UltraScale Plus, at least you get double the buffer space. Double the buffer, well, I guess it ends up being 4 times the buffer space. You're still only able to use half of the 32 KB, but it's it ends up being 4 times what you can use on the UltraScale devices. And then I figured the Stratix 10 devices, the Stratix 10 device and the Agilex F devices, which use the Intel FPGAs, which use the H-tile and the P-tile, were probably going to be a little bit better designed, because the numbers in the data sheet at least indicated that these should be able to get much higher performance, because these are a lot closer to what you would expect, considering how the buffer management is supposed to work. Because for both of these, you can fit, I think it ends up being less than 40 or 50 bytes of completion data per completion in the memories, which ends up resulting in rather high performance, because that means you can use the whole memory for when you're running at the worst case 64 byte completions. So, or most, yeah, you can use the whole memory, and that results in a much higher performance. So I went ahead and ran on these guys to just verify that the numbers listed in the data sheet were in fact correct. And it's a good thing I did, because I ran into a completion limit on the Stratix 10 MX at around 2432 completion data credits instead of 2500, which is what the data sheet listed. But I did hit the header limit at 780. So 770 is probably right for the header credits, but for the data credits, I'm going to go with 2400. And then with the P-tile, I ran into some rather interesting results. I got a limit of 4096 data credits, and I wasn't able to hit the header credit limit, because I was only able to coerce this thing into generating 1024 completions. And the limit is 1144 instead of 1024. So I know the limit is at least 1024 completions. But on the data side, this one is interesting. I suspect what might be going on is that the RX buffer could be shared between all of the different traffic types, because you have to store, let's see, the posted requests, non-posted requests, and completions separately. So what I suspect might be going on is that they have a 64 kilobyte buffer, and they kind of partition it into several different sections, one of them for completions, one of them for posted requests, one of them for non-posted requests. And that partitioning is logical, right? So the posted, non-posted requests, that is enforced by the number of flow control credits that are released. And then the number of completions, they just list the number of the data sheet and expect that you maintain the completions below that limit. But I guess it's entirely possible for one of these traffic types to actually eat up all the memory. So I've not been able to confirm that the limit is actually, this 1,444 256 bit completion credits, which corresponds to 2888 16 byte completion with data credits, which is the general spec for what that's supposed to be. But it's definitely going to be at least the datasheet spec, so that's good. And I've gone ahead and gotten that all loaded into the DMA engine, and that's all updated in the Upstream repository as well, based on these test results. So yeah, real quick conclusions here. The UltraScale definitely has a 64 CPLH limit, so the documentation is correct there. UltraScale Plus supports 256 CPLH credits. The docs are wrong about that because they say 128. But it's still not enough header credits based on the data buffer size, unless the RCB bit is set by the host, which is unfortunately not super common. And implementing the 256 CPLH credit limit does result in a small amount of performance degradation, but it's much more reasonable than having the limit set to 128. The data buffer size on both of the Xilinx cores, UltraScale and UltraScale Plus, includes the completion headers. So what we actually have to do is reduce the data credit limit based on the number of header credits. But that's not really a big deal. Let's see. And then on the Stratix 10H tile, that has a CPLD limit closer to 2400. Again, docs are wrong, but that's a pretty straightforward thing to fix, and we still get pretty good performance with that. And the P tile has very big buffers. Like I said, I haven't been able to hit the CPLH limit, and I hit the CPLD limit at about 64 kilobytes, which is above and beyond what the datasheet listed. So I haven't been able to verify that the datasheet number is, worst case, the best thing that you can get, but this does imply that, we can at least get, we should be able to hit that number, I think, under most circumstances. All right, so to sum up the status here, I've implemented the credit tracking in the DMA engine to limit the outstanding read request data. I've connected the RCB status signals. I've updated the example design with tests for the completion buffer, and then I've configured the 4 different cores as listed here. So the P tile, basically as per the documentation, for the H and L tiles, with this limit of 2400 that seems to be the case through testing. For UltraScale Plus, I implemented these figures here, where we have the completion data buffer size minus the number of header credits. Unfortunately, there is some performance penalty with the configurations of the Xilinx scores, but there's really not a whole lot, I think, that can be done about that, unless we want to handle not only drop completions under certain circumstances, but also potentially some corrupted completions here and there, because it seems like, at least on UltraScale Plus, when you overflow the buffer, you get some corrupted completions, which is definitely a bigger issue than simply dropped completions. The other conclusion, I guess, to draw from this is that Intel definitely knows what they're doing in terms of PCI Express, and their tiles really kick the pants off the Xilinx devices in terms of providing not only bigger buffers, but also more usable buffers, because you get more completion data credits per, you get a more reasonable matching between the header credits and the data credits, such that you can actually utilize the whole available buffer. Because the Xilinx ones, they give you 32 kilobytes on UltraScale Plus, but you can really only use 16 kilobytes of that because they don't give you enough header credits. But these numbers are much nicer for the P tile and the H and L tiles. I will mention that I did test on the PCIe 4C core as well, which is the Xilinx UltraScale Plus HBM parts, and that shows similar behavior to the PCIe 4 core. I don't have any Versal devices to test, so I don't know if they've improved this on Versal at all. I certainly hope so, but I don't know. And I also haven't tested on any of the other Intel cores. These are just all the ones that I have access to at the moment. But fortunately, running this test is a pretty simple thing to do, so going forward, if I get another board, I'm definitely going to be running these tests to make sure everything looks good. All right. So moving on to Corundum itself, I've gone ahead and updated the Upstream Git repository as of, when did I update it? Week before last, probably. A little while ago at this point. But this basically pulled in everything that I've been working on in my development repository over the past couple of months. So this involves a bunch of driver updates. All of the dynamic queue allocation stuff is now implemented. I added a bunch of ETH-tool APIs. And there's a bunch of other cleanup and improvements on the driver side that have all those changes have been merged in. I also added support for a couple of new boards. So like I said, the Zinc KR260 is now supported. I have one of those lying around here somewhere. I also have initial support for the Bitware 520N MX, although that one is running at PCIe Gen 2 because the FPGA on that board is kind of a low speed grade, which is unfortunate. At some point, we may be able to pop that up to Gen 3, but we'll see. I also have Ubuntu on Zinc support that was added for basically all the Xilinx Zinc dev boards. So I don't have support for, I guess I don't have Zinc support at all right now on the 250 SoC, but on the KR260 and on the two main Zinc dev boards, if you install Ubuntu on their little SD card, and then you can just build Corundum, load that on the SD card alongside, and run it. It works. So I got both the device. Mainly, I just have a script that generates the device tree overlay, and then you need that plus the bin file to copy that onto the SD card, and then everything pretty much just works. I guess there was a couple of little cleanup things I did as well. I guess this also kind of falls under driver updates. I think I added some reset management stuff such that for platform devices, the driver can now assert the reset line when it loads, which is useful to make sure that everything's starting from a clean slate, which is kind of important when you're dynamically loading this design, after the FPGA has been initially configured. I think there might still be a couple of wrinkles here and there that I need to look into. There was something wonky going on a couple of the boards in terms of making sure that the transceiver channels come out of reset properly and everything starts up after the clock oscillators on board have been reconfigured. So, and under some circumstances, you might need to basically load it and then unload it and load it again for everything to work when you're using Ubuntu on Zinc. So at some point I need to debug that and get to the bottom of what's going on there. But we do have at least initial support for that now. So that's, I think, probably the most straightforward way to use a KR260. And then for the other boards, it's nice not to have to deal with building Pay to Linux because that takes quite a while to build. Another thing I did is I added the virtual I2C mux. I guess I mentioned that probably last meeting. So this means that on a number of different FPGA boards that use some sort of IO pin muxing to select which optical module is the one you want to talk to properly expose that to the driver such that Linux can talk to the modules, you need some way of controlling those pins. And I added kind of a virtual I2C mux to a few designs that need that, and that's all implemented. It all works just fine. So that's all in the Upstream repository as well. And then finally, I have the PCIe RX completion buffer management integrated. So anybody that was running into hangs in relation to that, if you pull down the latest version of the code, that should have all of that buffer management implemented. So you shouldn't get a hang, which would be good. Right. So that's what I've done so far in terms of the Upstream repository. I think there's going to be a few kind of odds and ends that I'm going to commit over the next few days to fix a couple of bugs. I guess that was maybe just Wesley that reported a problem with one of the if defs in there, one of the kernel version if defs. So I'm going to take a look at that and get that fixed upstream in the next day or two. And I think there's a couple of other things. But yeah, what I'm going to do is leave the code in that repository more or less as is, with a couple of little fixes for at least another week or so here. And then I'm going to pull in a couple of changes that have been kicking around for a while that I want to stop rebasing all the time. And these are going to be potentially breaking changes to a couple of things. One change involves, well, the main change involves kind of reorganization of the queue control registers, coupled with some driver refactoring. So this does a couple of things. It adds these commands for doing kind of atomic manipulation of queue state. So instead of, reading and writing individual bits, you could just write these commands, or instead of doing like read, modify, write operations to set and clear bits, you can write these commands, and that will result in a bit being set or a value being loaded, something like that. And it should make things a little bit easier on the driver side, because you can just issue these commands. You don't need to do a read, modify, write operation, so you'll get better performance. And also, if you have two different entities doing stuff, one thing enables or one thing say disables the queue, another thing changes some other value, then there's going to be no concern about those stepping on each other, because that can be a concern if you're doing read, modify, write, and something else changes the same register. Then you can get in trouble. Another thing is that we're doubling the CQ and EQ control register density such that you can fit more completion queues on there. Because in the long term, what I want to do, this is not in this particular set of changes, but down the road, what we're actually going to do in Corundum is move to using queue pairs instead of separate TX and RX queues. And then the idea is for each queue pair, you want to be able to have one completion queue for TX and one completion queue for RX. So, keep all of the queues matched up. Having double density there is going to make better use of the address space. So this change is going to bump all of the queue control register block versions, and possibly a couple of other things. So that means any out of tree drivers, if anybody has a out of tree DPDK driver or whatever, that'll need to be updated to use the latest version of the code. But like I said, I'm going to push this change in a couple of weeks. So, heads up, you can go ahead and pull the repository now. And you should get code that works even with older out of tree drivers. But eventually, yeah, things are going to change. And then I also might push a couple of additional changes to implement a couple of other things in relation to the completion queues. So one of the changes that I want to make is to remove the distinction between RX and TX completion queues and just have like a single completion queue type. I have that implemented. So I think what I might end up doing is push that as well. I haven't made up my mind completely about that, just to get all of these changes taken care of at the same time. So now that the driver has support for the dynamic queue allocation, then that makes it a lot easier to do this consolidation where we just have a single CQ type. Eventually, once we have the queue pair setup implemented, then we're also going to do away with kind of the distinction between TX and RX queues. You'll just have queue pairs, and then each queue pair will have a TX side and an RX side. But that's a longer term thing. So I'm at least going to be pushing the queue register reorganization stuff, but I might also push a couple of other kind of related changes to the queue management project. Just kind of an FYI over the I'm thinking in a couple of weeks, I'll probably get this stuff committed to the Upstream repository, or potentially longer than that. But I just want to get that off of my plate. Right. And then what I've been working on most recently here is the Mac control and PFC layer. So the Mac control layer, it's responsible for exchanging Mac control messages, including pause frames. And this kind of has to be its own layer because this traffic is managed in a slightly different way than the normal data. And that's because if you're using pause frames, well, pause frame is going to pause the flow of data, but it's not going to do anything to the Mac control traffic. So this has to be integrated on the Mac side of the TX and RX FIFOs. Potentially it'll be integrated into the Mac module itself, but it could also go in Corundum. Not 100% sure at this point where I want to put it. I'm leaning towards I'll probably implement it in Corundum though, such that it's independent of whatever Mac is connected. So we don't need to have a Mac that supports PFC necessarily. We just need to make sure that well, and also we have less wires to hook up if it's integrated in Corundum, at the top level. So probably leaning towards doing that. In addition to the Mac control components itself, then I'm going to implement logic to handle the PFC frames and pause frames. And the idea is to be able to generate and receive PFC and pause frames using the Mac control layer. And then also to connect the pause frame RX side to the arbitration logic of the Mac control layer to basically block the TX traffic while the pause is asserted. PFC has to be handled deeper in the design, so that's going to be a to-do for a while, probably. I put together the modules in a somewhat flexible manner so that they can both be implemented in either the Mac module itself, so I'll probably pull them into the gigabit and 10G Mac modules that I have. But it can also be used independently for generating PFC frames and pause frames. So what I think I might do is integrate that into the L2 ingress and egress modules in Corundum. I guess one thing that I didn't put a bullet point down on here, but one thing that I'm building into this code is basically a fractional prescale value for the pause timing, such that even if you have even if you're not running synchronous with the NIC clock, you can still configure the correct timing for the pause frames, because all of the pause quanta are in terms of I think it's 512 bit times or whatever the line rate is. So if we put it in like the L2 ingress and egress modules in Corundum, I guess I need to check to see what frequency that's running at. That might be synchronous, in which case it's not a problem. But if it's deeper in the design, for example, you might be running at the PCIe clock instead of the Ethernet clock. So you'll have to have some weird ratio for the consuming the credits. So what I've done is I've implemented a fractional counter for that. So that'll allow you to implement a divider value that's not an integer and enable this to work correctly over longer periods of time and still produce the expected pause result. So the status at this point is that it's mostly implemented. Mostly implemented is in, I think I have the whole Mac control implemented and the receive side of the PFC and pause frames. I still need to do some work on the transmit side. It's mostly working in SIM, and then I got to get it integrated with the Macs and tested in hardware, and then also integrated into Corundum on some level. The plumbing is not there yet for PFC, but pause frames, I think more or less should work out of the box, although I guess I'll need to add probably a few additional control registers to test that and make sure it all works. Let's see. So I think, yeah, that's about all I got in terms of status updates for this week. If anyone has any questions or comments over, what I've discussed here in the presentation, fire away. Or if there's anything else anybody wants to discuss, fire away. I'll open up the floor to discussion now.
Yeah, Alex, on the completion credits change, did you use the output signals of the hard IP block that report the number of completion header credits and data credits?
No. And the reason for that is that indicates how many credits are available basically in the transmit direction, but we need to manage this in the receive direction. So those credits aren't helpful in this case. I am using those credits in the transmit direction to make sure that we don't have head-align blocking issues. But that's on the transmit side, not on the receive side.
Okay.
Yeah, I guess one thing that's kind of annoying about the Xilinx cores is that they actually have separate outputs that are supposed to give some indication of how much buffer space is available in the transmit direction, as opposed to just the raw PCI Express flow control credits. But every time I've looked at those signals, they haven't made any sense. Like when everything is idle, it won't be 0 or whatever, or won't be all ones. So
yeah.
So those are different from the main flow control credit signals that just report the PCIe credits directly. So
yeah, I have had to implement this for way long ago for Intel devices up to Stratix 5, I think. And I know the Intel cores did report the amount of completion credits you had on the RX side. And so I was just looking at the product guide 213. Okay. And it does say there is a flow control informational select input, which is a 3-bit input to the core that allows you to select between receive and transmit credits available.
Right. So I guess the problem here is that those are very, like not documented in terms of exactly what that's connected to. I don't know if the receive ones are talking about, what the core is advertising across the link to the link partner, or if that's actually, core internal. So, but with if it is in terms of what what it's advertising to the link partner, well, it has to advertise infinite flow control credits for completions. So, that number might not be all that useful. It just says, oh, it's infinite. Well, great. I guess I can pop those into the ILA at some point and take a look and see if they're doing anything useful. But I suspect that it might not help. Well, the other thing too,
I agree.
Is that the other thing too is that even if we're seeing, the occupancy of the RX buffer, that's not helpful because we need to know how many outstanding read requests we have even before the completions from those have ended up in the buffer, because we need to prevent the buffer from overflowing in the first place. So, by the time we see, oh, the buffer is getting full, well, if we've already issued more read requests and we have buffer space available, then we're hosed. So, but yeah, that is a good point. It probably wouldn't be hard to put that on the ILA and take a look. I think I have that hardwired just to look at the credits available on the transmit side, because that just seems to be the most useful one. But you could certainly cycle through and TDMA those values. The Intel devices, they tend to have a TDMA credit output where they cycle through all the different credit types on one port, and then you can pick the one that you want. For the Xilinx devices, you need to drive that and then look at the signals coming back the other way. So, I guess they each have their advantages and disadvantages, but yeah. Definitely using those in the transmit direction though. All right, does anyone else have any questions or comments about anything? I mean, if not, then I guess we can adjourn for today. The whole point of running these meetings, that if people have questions, then you can fire away. We can talk about stuff.
So one other thing I would like to mention is so we are working on this WireGuard solution, and we have maybe some. So it's a commercial effort. So maybe some parties have interest in DPDK support, and I think the MLA guys have already worked on that. So I had contact with them. They have just uploaded their latest sources for DPDK. They just told me on email, so I'll have a look at that.
That's cool.
And I'll probably have some. I'll ask them to update. I'll ask them if they can provide commercial services to update this support to match your latest changes. Because for us, it might be interesting for some of our customers. Because we are targeting 100 gigabit plus.
Right. Yeah. Definitely having DPDK support is going to be a good thing. I think I just posted relatively recently on one of the Zulip channels. Maybe it was a DPDK channel. Yeah. I actually found a couple of DPDK drivers that other people put together on GitHub, and I just randomly stumbled across them a couple of weeks ago because actually I guess that was May 29th, so like a month ago. Because the people who wrote those didn't send me any notifications or anything indicating that they'd put together drivers. I just randomly, I'm like, oh hey, Corundum DPDK. I'm like, what is that?
Yeah.
So yeah, well, that could be useful for somebody. I don't know how it compares to what MLE has put together.
Okay, yeah, because there is another one, right? An older one.
An older
made
one?
by Emily, I think. Made by some Chinese guy. I don't remember his name.
No, I think that might be the one that I found. The Leo W666
no.
Bruce, or was that the old one, or is that the new one? Basically, somebody put up a driver, and I guess it was good for a while until things changed, and then somebody forked that repository and updated it. Yeah, so it looks like that was the latest one that I found. Was this one says from a year ago, so it's probably this one.
Yeah, I find
I'll pop it in the chat here.
Much more recent.
Okay, I put a link. Yeah, so the other one is in the chat as well. Yeah.
Yep. I see the DPDK one. Yeah, definitely.
I've personally not worked with the DPDK yet, but it's something that some of our customers are asking for, mostly in a software-defined switch environment.
Gotcha. Well, I mean, that's kind of what DPDK is designed for, is the software switching. So yeah, coupled with Corundum, that could be a very powerful capability, definitely.
Sure.
Yeah, it would be cool to have both the Corundum device driver and the DPDK driver upstreamed at some point, but there's a bunch of changes that I have planned for the descriptor side and whatnot that are going to have to get squared away first. So
I'm already a DPDK maintainer for some cards, so maybe I can help here.
Well, it's definitely good to know what the process is for doing all that.
It's quite complex. They want to improve the overall quality, so it's kind of complex, and it's a big cycle to get anything in. But yes, definitely it's possible. Just take time.
Right. Yeah. Well, you've been doing some work with Corundum, right? Have you guys taken a look at the DPDK drivers that people have made available for Corundum?
Yeah, I had a look just on the code, but I didn't took the time yet to compile and to check. That's definitively on my to-do list for this month.
Gotcha. All right.
So it let you know.
Well, it's definitely something I've had people ask about here and there. Hey, when are you going to support DPDK? I'm like, well,
Mm.
some point. You want to
Yeah,
help?
yeah. Yeah.
Yeah, it's like a lot of the stuff that I'm doing.
That's on my to-do list. That and the
Yeah.
40 gigs, it's on my to-do list.
Right.
So
Okay.
yeah. Because I'm a heavy user of DPDK as well. So
Right. Yeah, I was going to say I don't do all that much with DPDK. I think most of the stuff that we're doing is we just want to be able to use normal Linux applications. So that means all of the fancy packet processing stuff we then have to do on the FPGA. I mean, part of that is for the research we're doing at UCSD, a lot of this is very timing critical. So the whole point is you do it on the FPGA instead of doing it in software, so you can actually get the timing right. But yeah, I know there's definitely a lot of people that would take advantage of a DPDK implementation once we have one operational.
Yeah.
So at some point that would be great. Yeah, I think Corundum or MLE put a fair number of cycles into working on a DPDK driver. I think they had a couple of different. They made like a slightly older version for an early commit, and then I guess they've updated that on their repository for, I don't know if it's the latest or something much more recent. I guess you said they just updated it recently, so it should be latest, presumably.
Yeah, I just had email contact with Ulrich, and he's going. I think they're even going to present some Corundum work they did tomorrow on the FPGA conference in Munich, Germany.
Oh,
I will not be able to join, but yeah, for people that are joining that conference, it might be interesting. And he just told me by email they pushed their latest changes to this link I put in the repository. Sorry, in the chat box. Yeah.
Right.
Yeah, it's quite recent. That's what I see. 22.11 is not the very latest, but at least it's not bad. Okay, let's see that.
Yeah, I'll take a look at the program for that conference. That's cool.
Yeah. How do you call that, Leon? The conference?
It just says fpgaconference.eu.
Okay. Oh, okay.
Yeah.
Gotcha.
Guess I'll
I
have
don't know
to
if
ask
there is a
them if
public
they...
video, but I might try to join.
Yeah, well, either way, I'll have to ask them, see if they want to present what they were doing at one of the dev meetings, perhaps.
Yeah, so yeah, that might be interesting. I put a link to the program PDF on the chat channel.
Yeah, thank you. I saw that.
What, in Zoom?
Yeah, in Zoom. I'm not on Zulip. Yeah.
Maybe you send that to me directly. I don't know.
Yeah, probably, because I'm not seeing. I'm like, wait a second.
Oh yeah, it might be directed to you.
Okay, but I guess they have a link on the site to the program.
Yeah, that's better.
Download PDF. Okay, there we go. Okay. Gotcha.
It's on the first day somewhere, fourth presentation, I think. I forgot.
Yeah. Looks like Ulrich is given a presentation, Corundum with NPAP. I think, what is that, their the stack that they have? Okay. All right. Well,
Fine. I
I
didn't
guess
know.
we'll have to see. We'll have to take a look at that. I mean, I'm not in Germany, so I can't actually attend in
Yeah.
person. But yeah, we'll have to see about the if they have video available, or they'll have a recording, or if they have a paper we can look at. I don't know. Well, I mean, Joachim, do you know anything about Ulrich's presentation?
It's here.
Ulrich's not on the call right now, but Joachim is, but maybe he's not paying attention. Oh, well, we can follow up with those guys separately, I suppose.
Sure. Interesting.
All right. Let's see. Is there anything else anybody wants to discuss for today? I guess not. All right. Well, going once, going twice. I guess we'll go ahead and adjourn for today then. And I'll see everybody in 2 weeks on, what did we say, the 17th, I guess, is 2 weeks from now. Yeah. All right. Sounds good. And
Okay, thank
everybody
you very
in the
much,
US,
Alex.
have a nice 4th of July tomorrow.
Yeah.
Cheers, guys.
Have a good 4th of July. Thank you.
Thank you.
Cheers,
All
Alex.
right.
Thanks for letting me tag along.
Sure. All right. Talk to you.
Cheers.